we are going to go over hybridization. So let's get started. Okay. So basically up to this point, we have been only talking about the localized electron model of bonding, and that's what we've been using to explain what happens in Lewis structures. So basically that assumes that electrons are going to stay close to the atoms from which they originated, and that bonds are from the overlap of orbitals. Okay, so to explain what we actually see experimentally, we have to have hybridization. So that's what we're going to talk about now. All right, so we're going to start by talking about methane, and methane is CH4. All right, so that is one carbon with 4 hydrogens bonded to it. Okay, guys, so what that means is if I was going to draw, and I'm going to come up here and draw it up here. If I was going to draw this structure, obviously it looks like this with carbon with 4 hydrogens bonded around it. Now, where are those electrons that are bonding? Those electrons that are bonding are in our outer energy level. So for example, if I'm talking about carbon, I have electrons in my 1s, my 2s, and my 2p. Okay. 1s is full, 2s is full, and that 2p is full as well. So my valent energy, like my valence shell, is where reactions take place. So that means for carbon, it's my 2s and my 2p sublevels where bonding takes place. Those are the electrons involved in chemical reactions. So, and then for hydrogen, so this is carbon, and then hydrogen, guys, hydrogen obviously only has the 1s. Sorry, I have to move that. So hydrogen only has the 1s orbital, that 1s electron. All right, so if we were thinking about this and we were thinking about localized electrons, what we would assume would happen is that the 1s of my hydrogen would overlap with one of the s electrons in my carbon, and then same thing. So I'd basically have 2 bonds that are s, the 2s overlapping the 1s, and then 2 bonds that are the 2p overlapping the 1s orbital of the hydrogen. So we'd have basically 2 different types of bonds. All right, so kind of that's what that's explaining in this first paragraph. So one of the bonds in methane would be formed from the overlap of a hydrogen. Oh, sorry guys, it's on shapes, not highlight. So we would think that the overlap of a hydrogen 1s orbital and the carbon 2s orbital. And our other bonds would be formed by the 1s orbital and a carbon 2p orbital. So then we would have 2 different kind of bonds. All right, but what we actually see is that all 4 bonds are identical. All right, guys, and so basically we have to have hybridization to explain why all 4 bonds are identical. All right, so what's basically going to happen then is for our bonds, our carbon is going to take these electrons that are available, all right, and it's going to kind of blend them together. So it's going to take that 1s orbital and then those 3p orbitals, and it's almost like it throws those orbitals into a blender and it blends them all together, and it becomes, instead of being s and p orbitals, it now becomes sp3 because we have that 1s and those 3p orbitals thrown in there. All right, so we have that sp3 hybridization there. All right, so yeah, so they're 4 identical. So again, so I'm going to kind of go through, I just drew it for you, and I'm going to go through what it says here in your notes. So we have the 1 2s orbital and the 3 2p orbitals, throw them into blender, out comes 4 new orbitals that are a blend of the 4 that went in. So they're going to have properties of the s and the p orbital, and we call them the sp3 because it's made from 1s and 3 p's. All right, and then it kind of talks through what the bond is going to look like. So any atom that has 4 effective electron pairs is going to have sp3 hybridization. Even if they have unshared pairs or something like that, they're still going to have that sp3 hybridization. Okay, Okay, so now let's look at the hybridization in ethene, the bonding in ethene. All right, so of our carbons, once again, all right, our carbons still have the 2s and the 2p, but here it's only forming 3 bonds. All right, so that means what we're going to end up throwing in our orbital is 1 s orbital and 2 p orbitals. So since we're throwing in that 1s and that 2ep orbital, our hybridization here is known as sp2, because once again, we just need to have those 3 bonds, we just need 1s and 2p orbitals. All right, so those are called sp2, and yeah. So now, guys, you might be thinking, okay, so every single time I'm doing hybridization, do I have to draw my electron configuration and think through where my bonding is happening? Guys, I've got good news for you. No, there is a little trick for hybridization. All right, and I'm going to share it with you guys right now. All right, so it's the hand trick. I'm going to attempt to draw a hand, and it's probably going to be really, really awkward looking. So here we go. We'll see how it goes. All right. Okay, that's the pinky. Oh, okay. Oh, yes. There's my hand. Looks a little bit more like a baseball glove, but that's okay. It's fine. All right, guys. So this is a trick to help you guys remember hybridization. So your thumb is S. Your index finger, I think that's called, is P. Middle finger is P. Ring finger is P. Pinky is D, and then the side of your palm is D as well. All right, and so we can use these fingers to figure out our hybridization based on how many things are bonded around our central atom. All right, so if there are 3 things bonded around your central atom, you have spp. So that would be sp2. All right, if I have 4 things bonded around my central atom, it's spp. So sp3. 5 things bonded around my central atom, sppd. So sp3d. So on and so forth. So that's just a little trick to help you guys remember your hybridization. And you can just use your hand to count your orbitals instead of having to draw out your electron configuration every time and figure out what orbitals are being thrown into the blender. So hopefully that's a helpful trick and something you can remember. All right, guys. So now what I want to talk about is sigma and pi bonds, guys. So what's happening in our bond is that basically we have the overlap of the 1s orbital and the sp2 hybrid orbitals of our carbon, and it results in something we called sigma bonds. And basically, sigma bonds, the orbitals overlap head-on, and the electrons are in the region between 2 nuclei. Now, that's not super important for you to understand, but what is important is that you know that every single bond is a sigma bond. All right, if you have a single bond, it is automatically a sigma bond. All right, and then double bonds and triple bonds all contain 1 sigma bond as well. All right, sigma bonds are just those bonds between the one orbital and the hybridized orbital. Okay, guys, but what you may have noticed is in this carbon, we only used up to sp2. So there's another p orbital there. So what happened to it? All right, guys, that extra p orbital that wasn't hybridized in our last example, basically those extra p orbitals from each carbon overlap above and below the plane of the nuclei, and it results in a sideways overlap that's basically called a pi bond. Okay, guys, so a pi bond only happens if there is also a sigma bond. So you have to have a sigma bond to have a pi bond. So pi bonds are not directly between the nuclei. It's not as strong as a sigma bond. It's weaker. But our double bonds contain 1 sigma plus 1 pi bond. So since our double bonds contain one of each, our double bonds are stronger than a single bond. So that's sigma and pi. Now, guys, it continues and it kind of talks through, the notes now talk through the hybridization of a couple more atoms. I'm not going to go through every single one with you guys, but I will kind of give you the basic rundown of them. So like right here, it has acetylene, which is C2H2. Now, guys, typically it'll ask when we're looking for hybridization, it's of our central atom. Obviously, in this case, we don't have a central atom, so it's just going to be either one of our carbons. So I'm going to look at this first one right here. I have just one of our carbons. I'm going to look at this one. They're the same, so they're going to have the same hybridization. But on this one, I have 2 things bonded to my carbon. All right, I've got a double bond here and a single bond there. So I have 2 things bonded to my carbon. So I have sp hybridization because I have sp, 2 things bonded to it. All right. And then between my hydrogen and my carbon right here, I have 1 sigma bond because I have a single bond. So that's a sigma bond. And then between my carbons, because it's a double bond, I have 1 sigma and 1 pi bond because it's a double bond there. Okay, so hopefully that makes sense. Guys, in the next 2 kind of examples, it talks about hybridization with the d orbital. Now, I definitely want you guys to read through it and know your little trick about sp, p, p, d, d, but I do want to make a note down here. So data from 2011 shows that d orbitals are actually not involved in hybridization. But it takes a while for discoveries that happen in the scientific community to show up in textbooks. So it's kind of starting to show up that hybridization doesn't occur in the d orbitals, but it's taking a while. So you may still see it in old test questions, but you will not see d orbital hybridization on the current AP test because it's been disproven. But it'll take a little while, so you may still see d orbital hybridization in other locations. All right. So for this one, basically, so this is just kind of a little summary. Sigma bonds are formed by the overlap of atomic orbitals between 2 nuclei. And then pi bonds are formed by the side-to-side overlap of those unhybridized p orbitals. Guys, here's what's important. This right here is what's important. Single bonds have 1 sigma bond. Double bonds have 1 sigma bond and 1 pi bond. And then triple bonds have 1 sigma bond and 2 pi bonds. Sorry. Okay, so now we're going to do some practice. I am going to do one with you guys and then leave the other 2 for you guys to do on your own. All right, so this first one is HCN. All right, so in this one, I have 1 hydrogen and it has 1 valence electron. Plus, I have 1 carbon that has 4 valence electrons. And finally, 1 nitrogen that has 5 valence electrons. So I have 1 plus 4 plus 5, which gives me a total of 10 valence electrons there. All right, carbon goes in the center. It's bonded to hydrogen and nitrogen. At that point, I've used 4 electrons. I still have 6 more that I can use. So I have 2, 4, 6 around my nitrogen. Problem with that is that our carbon does not have that full full octet. So I'm going to steal basically 2 pairs from my nitrogen and create a triple bond here. All right, so there we go. So first thing is it wants to know the hybridization. So I'm going to start with my carbon. I always do the hybridization of my central atom. So I'm looking at my carbon. My carbon has 2 things bonded to it. So sp, because we have 2 things bonded to it. So that means my hybridization would be sp. Next, I want to know bond angles. Since there's only two things bonded to my central atom, this atom has and no lone pairs, I should say, two things bonded and no lone pairs. This atom has a linear shape, so it has 180 degrees. Our molecular shape was actually the next thing. So 2 bonds, no lone pairs gives us linear shape. Guys, that's just from that Vesper chart that you guys need to know. And then last but not least, we want to know how many sigma and how many pi bonds. So since I have a single bond here, that means I have 1 sigma bond in my single bond. And then right there, triple bond has to have 1 sigma bond, and then it's going to have 2 pi bonds. So my total number here is that I have 2 sigmas, one from my hydrogen to carbon bond, and then one from my carbon to nitrogen bond, and 2 pi bonds. All right. You guys do the next 2. Pause the video now. Try to work them out on your own and restart it once you're done. Okay, so this is my Lewis, obviously right there is my Lewis structure for NO3. Since my N has 3 things bonded to it, it is spp, so it is sp2 hybridization. 3 groups around my central atom means 120 degree bond angle. And then I have a trigonal planar geometry. I'm going to have 3 sigma bonds because I have those 3 bonds, and then 1 pi since one of them is a double bond. And then over here with CHCl3, I have 4 things bonded around my central atom. So I have SPPP, so SP3. 4 things bonded around leads to a bond angle of 109.5 degrees. It's tetrahedral, and they are all single bonds, so I have 4 sigma bonds around my central atom. Okay, guys, that was hybridization. Hope this made sense.